I'm really excited to present this topic, something I've been very passionate on, which is bringing kind of a new way of thinking about refrigeration to our industry. So I'll introduce this digital twin software. It is a proprietary software to my company, so I apologize for products and things. I'm going to try and not focus on any of the branding that's involved with it, but really just focus on the essence of a new type of approach to using commercial and industrial refrigeration. So ammonia and CO2, as you probably know, are always ever expanding into new applications. These two molecules are actually two of the most abundant molecules in the universe. It's something I always like to think about, that other planets are trying to figure out how to use these molecules to move heat around. We have a lot of course, decarbonization, environmental regulations worldwide going on. So a lot of push for improving energy efficiency. I'm sure you know heat pump technology is increasing and is becoming more of a buzzword at conferences. In general, I would just say heat recovery and heat transfer using heat exchangers is becoming more and more prevalent. Refrigerant charges are very important as well to keep an eye on. This is becoming a bigger topic. So as a result, we're seeing smarter, more sophisticated systems, more electronics, also just contextually designed. So not just on loads, but also around the location, the job site, and heat-related opportunities. The point is that today is requiring more holistic approaches to our systems. It's really about how do we move heat and energy to where it needs to be. And for me, it's my task is, can I help us up our game? That's what I'd like to try and do with this software and this training. So the agenda, I'm not going to walk through this, but basically just to let you know, I've kind of planned to have it split into two parts. The first is more PowerPoint, and the second part is more example-based. I'm biting off a lot here today, I'll be honest, for a webinar, trying to introduce a new type of software and what goes into modeling. But also, to use it, we need to understand pH diagrams and cycles, because we're not just looking at components, we're looking at the whole system. And then trying to do a lot of live demonstrations as well with it at the end. My approach is really to try and entice a wide variety of people. So if you're in engineering and into modeling and designing, then I think it could be interesting. But I also tried to tailor this to technicians, end users, owners, operators as well. The idea here is not that you would have to create a digital twin, but if a digital twin was handed to you, how could you use it? So why a digital twin? Real quick through this. I can just say, with my own company experience, that component softwares do have limitations. Of course, they're myopic. They present data from their own point of view. And they're often used as a system software for good reason, that the compressor is often the one that does that. We're the ones generating mass flows, which is very important. But I will say that when it comes to system balancing and modeling, a lot of people are relying on rules of thumbs or guidelines. They use a lot of assumptions. And each of the components are unique. A compressor is actually fairly straightforward to model. It has pressures as inputs, and then power and mass flow as outputs. Heat exchangers are more complicated. There's two sides to them. There's multiple temperatures. Sometimes they're interacting with each other. So it has sort of a built-in iterative requirement. And of course, when you put these together in a system, it can really lead to a lot of iterations and a lot of challenges. I think doing this by hand and spreadsheets makes it really challenging. So this leads to potential issues, usually with assumptions or just confusion, because we're not really sure where did the superheat go. Was it in the evaporator or was it in the piping? Subcooling, same thing. Is it in the condenser or is it after? And I think also when it comes to CO2, I notice a lot of oversized systems. And I think that if we could be better at transparency with our safety factors with respect to product and heat influx, we'd start to see systems more optimally sized. The analogy that I try and use is a lot like kind of going from hand drawings to CAD, right? This is something over the last 40 years, I'd say, has transformed how we do engineering. A lot of challenges. It's not just all good. There's some work that has to be done, learning curves, but the benefits are really become company-wide, not just engineering that benefits, but procurement, operations, etc. So yeah, the benefits for a digital twin are comparable to the CAD, improving accuracy and speed, fast comparisons of system architectures, better understanding of cost versus efficiency, especially with heat exchangers, and reducing confusion, better communication. All of this leads to lowering the system cost and lowering your energy bill. I also think for end user technicians, you can really simplify troubleshooting if you have a digital twin at your fingertips. And I'm also hoping that it could be used to get rookies trained faster on the fundamentals. So let's see. So I'm going to be just doing some start off with a real simple example here create I'll say the simplest digital twin that you could make. If this was all we were doing, then it would definitely never be needed, but we need to start somewhere. And 3 components: compressor, condenser, the evaporator, and the expansion valve is connected with the evaporator. We connect it together. That's usually going to be pretty important for digital twin software with our world, because we have closed circuits. So we're looking to run calculations on conservation of energy, mass, etc. So what makes it a digital twin? I think first the visuality of it does. We're not just looking at a piece of paper with rows of data, but we can really see how the components are integrated. And then we can also get data freely. So we can really understand when we talk about capacity, we're talking about capacity at this component, not just in general condensing capacity, which can be ambiguous. So we can get data at the components. Also, the components is where the input should live and as real world as possible. So a compressor usually turns on from a rise of saturated suction temperature or pressure. So as suction pressure increases, the compressor turns on. So that's where the input is for that. A condenser, same thing. It's based on the relationship of the heat exchanger with the refrigerant flowing through it. There's a condensing temp established. And in the evaporator is where superheat is set. And then I think the other thing is just having flexibility. So as I said, this is a pretty simple system, but it's not too hard to start adding in pipes or regulators and be able to do more things. So that's basically just a quick intro as to what I'm talking about with the digital twin, and we'll come back to that shortly. So now that we have some insight into it, I want to shore up some of our basic knowledge, and also we just need to start somewhere. So I like starting at 0, and I apologize because I know a lot of you all know this, but we're going to move pretty quickly here. So as you know, refrigeration is when we use a fluid to absorb heat at one temperature and release that heat at a higher temperature. So we're moving heat against the natural flow. Hot and cold, I prefer to think of it as higher temps to low temps, because in our world we have a lot of levels of temperatures. Not just hot and cold. But I do like this diagram on the right because it's showing, when we think about a circle, especially when you think about the digital twin software, that you're really just seeing a circuit inside of what, right? And we have to think about this. Where does the condenser exist? Is it in a room, or is it outside? And the evaporator, is it in a room, or what else is connected to it? So in this case, we're showing it's in a cold storage room, and the condenser is outside, typical refrigeration arrangement. Okay, so we know we have cycle, then we need something to move this heat, and for that we use a refrigerant. So just to kind of put into perspective, CO2 and ammonia are very, of course, great refrigerants, and I've got 410A and 134A also here as reference. So this is showing pressure, temperature, pressure on the y-axis and temperature on the x-axis, and these are the saturated temperature curves of the refrigerants. And this is atmospheric pressure here, so I actually like to kind of start with, I don't have a point in here, but at 212 degrees in atmospheric pressure, this is where water would boil. So right where the 717 is where, if we had water mapped on here, that's where it would be. So kind of puts into perspective, for me, puts context into what a refrigerant is, and that is it's boiling at a much lower temperature in comparison to water at atmospheric pressure. And then when you look at these, you're bookended by your triple point and critical point. But in here, all of these fluids have something in common, which is that their temperatures are in pressure ranges that we can work with. And so that's the important part of CO2. it often gets talked about having very high pressures, and it does in comparison to these other refrigerants. But the most important thing is that it's in a range that we can work with, and out of this, and especially with CO2, it has a lot of opportunity. So with the refrigerants, now we need to better understand them. And to better understand them, we can use a pH or pressure enthalpy diagram. This is a really simplistic view of it, but we have vapor on we have a vapor dome that describes the phase changes. So to the left is where the refrigerant would exist as a liquid, to the right as vapor, and inside as a mixture. And above this is the critical point where supercritical fluid is. So pressure on the y-axis, and then enthalpy, which is our BTUs per pound, so our energy per pound of the molecules. This is now a little more detailed, but I think it's important to note this is a map of refrigerants. So, and it was really important, really valuable for engineers, is because with this map, with any state point, we're pretty easily able to find other state points. So if we have pressure and temperature not inside the vapor dome, we can find entropy and enthalpy pretty easily. If we're under the vapor dome, then we need maybe something like quality and temperature to match up. I also like this drawing because it shows the liquid line and the vapor line separate. So the liquid line is blue, and you might also know it's called bubble point line, which is not always intuitive, but just think about you are starting out liquid and coming into the vapor dome, and this is where the line where you will start to create bubbles. And on the right side, you're starting out as a vapor, and as you come in through the red line, you start to create droplets or dew. Quality goes from left to right as a function of vapor. So 0 is all liquid, and then as it moves to 1 or 100%, it's vapor. Pressure and enthalpy we covered, and then temperature has these sort of S lines where liquid comes very vertical, and then temperature moves across the vapor dome in harmony with, as long as the refrigerant is azeotropic, but in harmony with the pressure, and then afterwards drops down. These are really the main ones that I think that are worth focusing on. You can obviously, as I said, it's a map to get other data. So for density and specific volume and entropy, it's also there, but usually it's not. I probably won't reference those parameters too much in the rest of this presentation. Okay, so now that we have our refrigerants, we can start to walk through what the molecules are going through and what they're experiencing by putting this Carnot cycle overlaid the map. So for example, the refrigerant is compressed, and then it passes through the vapor dome and it's condensed. Then it is expanded. Expansion is called isochoric, so it doesn't change any energy, it doesn't lose any energy. So you can see the enthalpy stays the same, and then evaporation to the right. I like to, when you're doing a digital twin software, I highly recommend keep it in this flow. Even though these are not pipes, it does help kind of our brains think in that direction. And just when I say that these are not pipes, meaning you can't tell by the length of these lines what's going on, right? So for example, a liquid comes out of the condenser and is just shown as a point, but that could represent hundreds of feet of piping. We don't know. The other thing about this is we don't have a time aspect. So there is no way of knowing what mass flow is happening. And we also don't know what the heat exchanger efficiency is either, right? We just know what the inlet points and the outlet points are, but we'll need mass flow to do that. So let's take a look a little closer at heat exchanger capacities and what influences them. So this is zooming in with ammonia still, and that's important to note. I've got the temperature lines on here as well, called isotherms. And here you can see how close together they are in the superheated region. So not a lot of available heat in comparison to the amount of temperature that you'll drop. Whereas in the condensing section, we're not changing, the temperature is constant, and we have all of this latent heat available for us for heating. And then at the end of a condenser, especially if it's shell and tube, for example, maybe you have some subcooling taking place. Again, we don't know on the pH diagram if this is happening inside the condenser or happening externally. And then the evaporator is unique because we have this, if we have the liquid temp, we know where our enthalpy is, but we need to cross-reference it with the pressure to find out what the quality is. And I also think that's a really important property that technicians aren't often paying attention to is what's the quality coming through these expansion valves, because that often affects the performance of downstream components. And then superheat, again, similar story as I mentioned before. Is this taking place inside the evaporator or outside? We'll need the diagram to cross-reference to be able to tell that. The nice thing about heat exchangers is and especially with latent heat change, it's a pretty easy formula. And I would actually say it's just one formula. I'm not going to go through any other formulas today, but I actually think it's really worth committing to memory if you haven't already. And the reason, because it really helps drive home this important function of the compressor, which is mass flow. So so just to review the formula, capacity is equal to mass flow times change in enthalpy. So if I have the enthalpy exiting this evaporator and subtract it from the enthalpy entering and multiply that by my mass flow, then I'll get my capacity of 150,000 BTUs. So really just driving home that, with a digital twin software, we can see how much the mass flow is really driving this. Whereas with component softwares, we're often using the compressor software because it is the one providing the mass flow. But we're often not seeing where exactly are these capacities taking place. So let's go back over to our demonstration. So in this system, I'm just going to kind of focus around the evaporator. And you can see we have about 6,200 pounds per hour going through this compressor and through this evaporator. And we have no superheat and no subcooling right before or after it. So the net capacity is equal to the total capacities. So let's add superheat to the pipe after the evaporator and see what happens. So this has 18 degrees of superheat added. And I put this as comparison to the previous system. And you can see that all of the capacities went down. Even though we're adding some heat in here, parasitic heat, it's not going to increase our heating because the ultimate driving factor was the mass flow, and the mass flow went down. It went down from 6,000, I think it was 6,200 down to 5,868. And the reason is because we superheated the gas, which made the compressor reduce the density entering the compressor, and that reduced the volumetric flow rate. So as a result, all of the capacities were reduced. So let's look at subcooling. Similar situation, but a little different. Here, we don't have a change in mass flow. We're still at that 5,868 because this has no bearing whatsoever on any of the inputs that affect a compressor. However, we did get an increase in cooling capacity, both from a net and a total. And we also got an increase in heating, but not a net. And why is that? Well, because this pipe is not inside the condenser, it's after. So yes, there was heating provided, but we don't know if it was in this case, we know it was not in the condenser. But from a total standpoint, theoretically, this was available. Just to drive this home, so I'm looking at 4 different capacities, and I think this is something I'm trying to illustrate. We often look at systems as only cooling or only heating, but every refrigeration system out there is doing both at the same time. It's just a matter of perspective. So the net is what's taking place in our process. It's what we care about. It's what's inside our heat exchangers, usually evaporators and condensers. It could be more. It could be something sensible. It doesn't have to be a latent heat change. But for the most part, you're going to find net is referring to our evaporators and cooling for evaporators and heating for condensers. And then the total is what's potential. So maybe there's an external influence or parasitic heat loss or heat gain. And so this drives our total capacity. So again, 4 numbers there, and it can be very confusing when we get with more complicated systems. What exactly are we focusing on? Wrong button there. Okay. Let's look at some more complicated architectures and how they are processed to a pH diagram. So in this situation, we're looking at CO2 with a supercritical gas cooling going on. And then this is a nice diagram because it shows that whenever you see these vertical lines, that's an expansion. So we have expansion valves, just a straight drop in pressure with no change in heat capacity. So here we have an inlet pressure regulator, often called the high pressure valve or high pressure regulator. Because we have supercritical gas, we don't have a liquid seal. So we have to create a valve. We have to have a valve here to make sure that we maintain pressure in this gas cooler. Of course, we don't want to operate this high pressure throughout the whole system. So with CO2, we are often using open flash technology. The ammonia guys should know this very well. It's been used for forever in ammonia. And CO2 is a very similar concept. A is the entrance. And because we are expanding into the vapor dome, we have two-phase flow. And this splits so that our exit out of the C should be all dry, so out of the right side of the vapor dome, and out of the bottom of the vessel should be B, all liquid. So this is what's called liquid vapor separation, and the velocity through this vessel matters to make sure you have proper separation. Okay, the liquid then goes through expansion valves. And again, I'm just trying to illustrate, you can't tell that there's 2 lines there, but we know that they are because we have one feeding a medium temp evaporator and another feeding a low temp evaporator. And then the other valve in the system is the flash gas bypass valve, which is another inlet pressure regulator that maintains the pressure on this vessel. Again, very, very well known in the ammonia world. Often this would be referred to as controlled pressure receiver from the ammonia side. Okay, last few slides before we switch over to all the examples. I just want to talk about ammonia and CO2 a little bit more because they are unique animals. You probably know the facts that are here, and I'm not going to waste time reading these out. The capacity difference is probably the other one that's most well known. So up to even 7 times difference, meaning you get more capacity, more bang for your buck from a displacement with CO2 than with ammonia. All of this is due to the density of CO2, and we'll talk more about that. This is a nice slide too, to just kind of show how CO2 has sort of a special ability. You can take advantage of its pressure drop and not lose a lot of degrees in your heat exchanger. So even, 3 or 4 pounds pressure drop would only be 1 degree of penalty. You still penalize your mass flow, but you don't have the temperature penalty in the heat exchangers that you would with that same pressure drop with another fluid. And I always like the slide. It's from the late great Pega Herniak, and it just has a really nice comparison: 134A, ammonia, CO2, and propane, but how they relate to each other to scale. So here the enthalpy has been scaled together, and it just really shows how the latent heat of ammonia is so expansive. And CO2 is the other end of the scale, right? It doesn't look like it can do anything, but we know it has more capacity than ammonia, and all of that, of course, due to its amazing density. One thing I forgot to mention earlier, but it's an important note: don't ever compare enthalpies from pH to pH. So enthalpy is always about change in enthalpy. It has to be relative, but it's not an absolute value. So the absolute value of enthalpy is not something that's going to translate from one refrigerant map to another. And the last point about CO2 and ammonia is just hammering home again the density. This is just talking about the density gradient. So, if you look at the difference in density of CO2 vapor versus CO2 liquid, you can see it's much closer together. And of course, this is where it becomes supercritical and basically merges and becomes the same density. But this is just important to note. It just behaves differently. And I think when you're coming from the ammonia world, this is the type of things to think about. Not so much the fact that CO2 has high pressures, but that, which I mean, it does, and that's often, I will say, talked about probably too much. I think what's more interesting is the high density, and this relative between vapor and liquid is important, especially when you think about liquid vapor separation and carrying, droplets down a pipe, especially back to a compressor. Okay, so now I'm going to move. I think we're running pretty good on time here. Yeah. So I'm going to move over to the exercises. And again, just trying to pick out some different concepts. Nothing here I would say is perfectly done, but I just want to show a few different ideas on how you might use the software from different points of view: end user, technician, engineer, etc. So one thing I wanted to kind of continue on with that comparison of CO2 and ammonia, one of my favorite things to point out with the differences of this, and it goes back to that open flash, is there's a, very, you won't always often see these valves included in modeling softwares, but we know they're out there in real life. So this valve is holding back pressure in my controlled pressure receiver before it feeds the echo port. So we have a pressure difference here, and we can see this on our pH chart. And I'm sorry it's not zoomed in a little far away, but you should be able to tell that when we have this pressure drop, it's expanding into outside the vapor dome. So we're getting dry gas there. So that's kind of a nice thing about ammonia that we don't always, we often take it for granted. Any pressure drop along this line, anything like that, it actually would add more superheat and make it safe for our compressor. In contrast, let's look at CO2. So CO2 here, we have a flash gas bypass. Same concept though. We're monitoring the maintaining the pressure in this vessel. Let's look at that expansion. Yeah, and you can see with CO2 we're operating much higher in the vapor dome, and so when we expand, we're actually getting wet, about 5% wet. So not like a lot, but it's still enough that could really again do damage to components that we don't want to have liquid. So this is why you'll almost always see these two lines married together with a heat exchanger. So now, again, after the valve, we can see it's two-phase. If you use the legend, you can see this is two-phase. And then exiting the heat exchanger, we now have about 31 degrees. So about 8 degrees of superheat exiting this heat exchanger now. On the pH chart, it actually doesn't look that different because we knew it was getting superheated, but now it's adding a little more superheat. And this line, this second leg of compression is now kicked out a little bit further to the right as thanks to that additional superheat. Okay, let's move on to the next example. And this is looking at heat reclaim. So if this was, a shell, this is, by the way, an ammonia system, two-stage, 4 different compressor groups. So a lot going on. Computers been up now. Let's close some things. Okay, looks like I'm back. So as I said, there's a lot of stuff going on here. And, if you had a shell and tube condenser, let me see what we've got this set for. So first I like to kind of figure out, if I had this, say I had a facility and I wanted to look at this and kind of examine what's going on, you could model up your capacities and pressures with the rest of the system, set your inlet temperature and outlet temperature. And then you'd find out that your flow rate, sorry, to zoom in, your flow rate is predicted to be 1400 GPM through this condenser. By the way, this is not this is not a known condenser. This is just a dummy. And this is all just based on using this capacity data and using fluid properties. So we know the specific heat of water, density of water. Then we can come up with all these other great calculations. So, and also play around with things. So like I said, if you're an end user and maybe you wanted to, see what happens when you reduce the flow rate. So I've got, sorry, that was way too much, 750 gallons per minute. 750 gallons per minute creates 94-degree water. And you could, reduce that even further and see the implication. So again, not a very hard calculation. Certainly, I know a lot of you could do that on a spreadsheet easily. But it's the idea that it's connected to so much at once. And so as you're making changes throughout your system or maintaining, you could keep this alive and be able to really make optimization changes and understand the implication of decisions. Let's look at heat reclaim on the CO2 side. So here, instead of using a water-cooled gas cooler, let's just add in additional heat exchangers. This is kind of an interesting situation too, because we have one compressor operating at a much higher pressure than the other. So as a result, its discharge temp is much lower. So this is still, could be a lot of available heat, especially if there's a lot more mass flow, which there is, running through this lower temp side. So what about if we added a heat exchanger just to that compressor? And we can choose temperatures that, optimize based on that discharge gas temp. So it's discharging about 202 degrees. So, and I'm just making these numbers up, but I've got 130-degree water entering and 180-degree exiting. And now I can see what my volume flow is and also what the expected outlet temperature would be with that size heat exchanger. And then we could also add one here as well and see how these interact together. So this one we'll set a little lower, 85 inlet, outlet 130. You can, once you maybe you design this for a change of -50 degrees. So you know that was 300,000 is what it sized it at. You can switch your inputs around to 300,000. And then, maybe say, well, let's say what happens if I get roughly half the size heat exchanger? What's my impact? So again, nothing that's one at a time, not too difficult, but really, really quick, lots of information and using a more comprehensive system. All right, the next example is going to be just focusing on liquid vapor separation. So this is more of an ammonia example here, but you can see, so we have a economizer open flash vessel similar as before, where the dry mass flow is going into the echo port of a screw compressor. And you can see that we have really a incredibly oversized vessel. I have 977 pounds per hour of refrigerant exiting, but the max for this vessel is 6,000. So we could probably reduce the size of this quite a bit. Let's try 16 inches. And yeah, a lot of room there to work with. So really easy sizing there. And then down here we have a recirculator vessel. Now it looks pretty well used up, 91%. So the mass flow exiting is about 8,000 pounds. But what about if you're at a facility and you've got this maybe a coil inside and you want to take advantage of this coil and put and put 40 tons of heat into there. Well, that's going to increase the amount that needs to boil off, and now we're over the limit. So this is also cool. In this situation, we could drop the level of the vessel, because it's a horizontal vessel, and if we drop it down maybe 10%, then we can see, oh, now we have a little bit more diameter, more room for my velocity of the gas going through there, and that increases my available separation. And so now I'm only using 83% of what's available. Okay, the next example I wanted to do is going back to CO2 and looking at it from, the lens of I think one of the things that's always new for technicians to learn with CO2 is just the mixture of mass flows, right? I've got a low temp group in this situation, and this is kind of a conventional supermarket type CO2 system, but I have a low temp group down here, which we'll just ignore for now, and focus on the medium temp, and then my flash gas. So if you think about it, you have three mass flows coming together. Usually your low temp is going to be pretty hot because it's the discharge of the compressors. Your medium temp evaporators are, I'll say, in the middle. They should have some superheat, some pretty decent superheat from their cases. And then as we talked about earlier, this gas returning from the flash gas vessel could be wet unless this heat exchanger is doing its job, which it looks like it is. So in this situation, let's just say that we were trying to understand why, though, our superheat at this compressor is only 11 degrees, and we'd like to see it maybe a little bit higher, just for periods of defrosting in other situations. So this medium temp group, we don't have to model it just as one evaporator. We can model it maybe as more in real life. So see how the cases come together. EPRs, setting the pressure 35 degrees. This one's setting to 27 degrees, 22, 20 degrees. And so now we can really get more information, velocities, temperatures, and maybe helps focus on, oh, you can see this is two-phase here. And yeah, I forgot to set the superheat in that evaporator. The thing I want to talk about here for a second is just when it does come to modeling, and this kind of goes back to my analogy with hand engineering drawings moved to CAD. This is actually a little tricky here because I just have one inlet and one outlet, and then I have to divvy up all of my mass flow to these different evaporators. So if you know CAD, then when you're doing hand sketches, you have to define your sketch and your assemblies in a very particular way so that it's exactly constrained the right way. You can't put a right, if you're drawing a square, you can't dimension every single line and also say that every side of the square is equal to each other, because now you have two constraints that the computer is trying to deal with. So that's kind of similar here. I've got, when I have these multiple mass flows in parallel, it's pretty easy though to create sub processes. So I'm driving mass flow through this heat exchanger by just forcing it. So I'm going to put in my required capacity and see exactly that mass flow through these evaporators. And then this last one is floating. I think, for me, when I was learning CO2, I just wish I had had something to really, when I'm at a store, I just really wanted to walk around with the temperature gauge and just really try and understand all the temperatures and pressures that are going on. It's very intimidating to walk into a supermarket for the first time. A lot of pipes going everywhere. And I just wish I had something like this to kind of match up with this pH chart, especially, a lot going on here. But again, it helps give me visualization, helps me understand a little bit, especially, I've got an example, we'll talk about low load, right? So in here, as this pressure line drops, CO2 really has big influences on that. And so it's just nice to be able to have something that you can, smell, touch, feel yourself, play around with, and kind of explore what's going on. For the ammonia side of this exercise, I just thought I'd grab something really, like a really big system, just to kind of show how you could have a lot of compressor packages. This has got what, thousands of tons of cooling going on, and they're all integrated. You've got vessels, intercool. That's another thing that's I think is neat as well with ammonia, is to have an intercooler. Something that I think I'd like to see more of in the CO2 industrial is to bring in, to maintain a discharge, a suction temperature, by bringing in just a little bit of liquid into a vessel and being able to maintain a really good return gas temp. I think this is a really cool idea I'd like to see explored more. By the way, just going back to this example, I don't know if you ever met someone who wants to talk about adding superheat or adding heaters to a suction accumulator in case you're having wet gas back to a compressor. This is often, sometimes you'll meet someone who's like, hey, well, let's just put a heater around it, or a belly band heater around it. And crankcase heaters, I would say just about any heater you plug in, this is only going to be effective in a standstill situation. So you can see with a system as large as this, if we put 300 watts, which is about 1,000 BTUs per hour, you're only moving the refrigerant like 0.2 degrees. So it's very, very much not. It's only for a static situation. It would never be used in an actual running system. Okay, a couple more examples, and I think we should have some time for questions. Yeah, here I just wanted to kind of look at, oh yeah, this is neat, pipe velocities and going from full load to low load. So this is a CO2 system, gas cooler running pretty high pressure, 1225 discharge pressure and 89-degree outlet temperature. And just kind of zooming in on these pipes here, you can see that I've got 27,000 feet per minute going through these pipes. That's probably because the default was an 1/8 inch. So I'll pick a wheel end for one of these. Let's do 1 3/8 and Mueller keep top. Okay, so now we have some more reasonable velocities. And also I went ahead and preset some thresholds in here. So I'm just using a minimum of 1,500 feet per minute, a max of 4,000 feet per minute. That's not a recommendation, by the way. I'm not here to tell you how to design your systems, but I think you probably have your own velocity ideas. And so it's kind of nice to have, the sizing summary tells me that, let's take off the evaporator. Just kind of look at these pipes, these two pipes that I'm in my range, a little bit the low end. And let's see what happens. So if we go to a low load condition, right? So right now we have 180,000 BTUs in this evaporator and 850 in this one. Low load, maybe they cut by a third. Maybe this goes to 80 degrees condensing. So as a result, you can see the velocity now is really decreased in these pipes, as you'd expect. So again, stuff that I know you guys can do, but a little different way of doing it. And also you can imagine in a really complicated system, especially like something like this, this sizing summary is really great for just going through and gut checking a lot of things, not just velocities, but pressure ratings, sizings of capacities, et cetera, et cetera. Okay, and one last example here is with the ammonia world. So I think this is also something that might resonate with some folks out there. This is using two different compressors at split suction. So we have a +20 and -20 going to an oil separator. And the oil separator is, again, we'll pull this up. we can see that the oil, we have a lot of problems, I'll say, with the system. The screws are not receiving the oil temperature that they need. So the oil entering the screws is too high. The refrigerant mass flow in the separator is too high. And the oil cooler is sized correctly for the moment. So let's see what happens here. We're going to increase the size of the separator. And also we'll look at this mixing valve temperature, and it looks like we need 131 and 145. So I'll make it set for 130. Okay. And now it's telling me that my mixing valve temp is not able to keep up. So if you look at this, this is in this component, which is an actual heat exchanger. So this is I like showing this because there's a lot of possibility to merge heat exchanger curves in with the software. And in this case, we do have it here. The oil comes around and has a bypass around, and then the oil cooler calculates what it can do. So in this case, it's outputting 133 degrees, but we needed 130. It also has 14.5 pounds of pressure drop, which is way too high going through there. So we know we can increase the size of this, and then we'll see temperatures. Outlet temperature of the actual heat exchanger is 119 degrees. The mixing temp is set for 130 and is able to meet that by mixing 84% cold with 16% hot. So now we're clearing up a lot of things here in our sizing table here. And the last piece is this is a thermosiphon oil cooler. So we have a thermosiphon vessel that is gravity feeding down to this oil cooler. And it looks like I don't have a big enough volume to maintain sufficient cooling. So I need 3.28 cubic feet instead of 1.57. So I'll just increase this diameter. And I like ending on this because it's a little humble for me. When I was working in this and developing this for the first time, I actually could not figure out why the balance of this vessel wasn't working. And I realized I had never really paid attention to the thermosiphon vapor needs to go back to the start of the condenser. And I've never really paid attention to that, but it's quite a lot of mass flow. I know the industrial guys, system guys, of course, you know this, but me from the compressor side, I never had to worry about this, never had to think about this. And so it's just a really good example of how when you start to work through these softwares and go through them, how, not only are you giving yourself new functionality, new features, but I think most importantly, you're just giving yourself a better education. I think that's a good thing to end on. So thank you guys again. It's always interesting to do a webinar and a bunch of empty faces, but hopefully this was something that you found beneficial and interesting. So thank you again. And if we have any questions, I'll be happy to take them.